we will be talking about interferometry of light waves. So basically this is optical interferometry. Now we know that when two waves, for example, if these are two light waves, by this time we know that if we draw light waves like this, these are nothing but the locus of the tip of the electric vector as it oscillates. Okay, and this is a propagating wave. Now, if we overlap these two waves, for example, if these two waves are exactly in phase, the second wave may be something like this. Okay, and if we make them overlap, then the resultant amplitude is simply the algebraic sum of their individual amplitude. So if I draw the resultant amplitude in green, the resultant amplitude will maybe look like this. Okay, this is the resultant amplitude. So we see that we have in certain regions we have amplification of amplitudes, and this is in fact interference. So as you can understand, the result of interference would depend on the phase difference between the two waves. Okay, for example, if they are separated by pi phase, which is one goes like this and the other is something like this, and they have equal amplitudes, the algebraic addition of them would give you 0. That is, you have 0 output, no light at the output. The result of interference would be completely dark. Okay, we are going to explore this in a little more detail. The first condition for interference is coherence. Now, what is coherence? Well, when we say two wave fronts or two waves are perfectly coherent with each other, we mean that they have a phase correlation between them. Now, if we want to expand this idea further, if one wave is like this, okay, this is now what I have drawn is a perfectly monochromatic wave, a perfectly sinusoidal monochromatic wave. But we must understand that a sinusoidal, perfectly monochromatic sinusoidal wave does not exist in nature. Now, this wave has a single wavelength, a single frequency, which means if we plot its Fourier transform, or forget about Fourier transform, if we plot the frequency, it would just be a delta function here, just a single line. This is a frequency, certain, let's say lambda naught. Now, in practice, we never get a single frequency. Okay, it is always a band of frequencies that we have. The band may be narrow, the band may be wide, okay, but it's a band of frequencies and it has a spread. So the frequency has a spread. Okay, let's say this spread is delta nu, which means that the wave that you actually have is not a sinusoidal wave, but it has a number of frequencies, very close frequencies with, sorry, just hold on for a minute. Yeah, it has very close frequencies with these amplitudes. So this is lambda 1, lambda 2, lambda 3, lambda 4, infinite number of these frequencies. They overlap together to give you the shape of the wave. Okay, and this curve is usually Lorentzian or Gaussian. This happens due to the process of emission of light from atoms. And if we now attempt to, well, combine these frequencies together between, well, central frequency being mu naught and with an extent of delta nu, you will see the resultant wavefront does not resemble a monochromatic wave, does not resemble a sine curve. It will look like something like this. okay, and so on. So this is the wave that keeps on propagating. Now this is not a monochromatic wave, and here you have a larger amplitude, so you can, although this is not correct, but you can conceive these as wave packets, okay, large concentration of photons, and here in between them the phases change randomly, okay. In between these wave packets, as you see, the phases change randomly, and therefore if the phase changes randomly, and the phase changes randomly means it changes at the rate of 10 to the power 9, 10 times a second, very close to the frequency of light. That is to say, if we, the phases between 1 and 2, these 2 points, or phases between, let's say, A, if this is my point A and this is point B, the phases are completely random because the phase is changing randomly here. Now what happens if the phase changes randomly at a very fast rate? What happens is, suppose the phase at some instant is pi, okay, you get a dark fringe. At the next instant, it's a multiple of 2 pi, you get a bright fringe. And if this is happening very fast, and it can have any value between 0 to 2 pi, so next instant the wave is like this, second wave is like this, okay. It can go on changing like this for at a very fast rate of 10 to the power 9, 10 times a second, and there is no detector available in the world to look at these changes, to follow these changes. So what we will get is simply a uniform intensity of light, okay. This is called incoherent superposition. So we see incoherent superposition, for example, when we shine two torch lights on a screen, we see incoherent superposition. There are no fringes, but we have to remember, there are no fringes, it doesn't mean that there are no fluctuations of the light beam. There are fluctuations of the light beam due to interference, which is happening, which is vanishing, or which is changing at the rate, at a very fast rate, which our eyes, neither our eyes nor any detector can detect. So we can only detect interference effects if the phase difference between two beams are constant. Then only we can say we will have a bright fringe or a dark fringe for infinite time, and we can record those fringes, right? So the first criteria is to have a coherent beam of light. Now incidentally, for sunlight, if you calculate, the sunlight is a very large spread, and the line width, this line width is about 10 to the power 14 hertz, okay. For a laser, it's a very small amount. Now what happens is, as the, for if this is my spread for the sunlight, then the spread for a laser may be something like this, which is very narrow, in fact narrower even, okay. Maybe very close to a delta function, but not exactly a delta function, it will have some spread. So for a laser, this pattern may look like this. It goes on and on. It can, for very good lasers, stabilized lasers, it can go on for kilometers and then die down. Here you have a random change of phase and then again continue. So for our purposes, this length of wave packet is coherent, okay. This is almost monochromatic, so we say that laser is a monochromatic beam of light, okay. Now let us see what happens in interference. So let us say we have two light beams, and let me represent these light beams by let's say A with the amplitude of a light beam, and we'll express this phase in terms of exponential. It is I into kz minus omega t minus delta 1, okay. So k is the propagation constant, 2 pi by lambda, omega is the cyclic frequency in radians, t is the time, z is the distance of propagation, and delta 1 is the initial phase. Okay, and let us say we have another beam b e to the power I kz minus omega t minus delta 2. So their epochs or initial phases are different. Now let's say these two beams are interfering. So they are adding up. Okay, so we will write a e to the power I into kz minus omega t minus delta 1 plus b e to the power I into kz minus omega t minus delta 2. This is the resultant amplitude. But then we cannot see amplitude, we can see only intensity. Okay, all detectors, all photodetectors, light detectors can only visualize intensity. It cannot record amplitude values. It cannot record phase. The phase part is completely lost. Okay, so either it will be the square of this. I mean, you can take the individual squares and then add them, square modules of this and this, or it can be, well, let me write it, let me write it once again. A to the power I into kz minus omega t minus delta 1 plus b e to the power I into kz minus omega t minus delta 2, the square modulus of the addition of two intensity values. Now, which is correct? Well, in case of incoherent beam, this is correct. The first one is correct. This is in case of incoherent light. Why? Because their phases are changing randomly. Delta 1 and delta 2 are changing randomly. Therefore, they have no phase correlation. And because they have no phase correlation, the result will simply be the sum of their intensities. Okay. If they have a phase correlation, which means that if the two beams, if the phases delta 1 minus delta 2 is constant for all time to come, then we say that this is coherent. And in case of coherent light, we simply add up the, in case of interference, we add up the amplitudes and then take the square modulus, because that carries some meaning. Why? Because the addition of amplitudes means addition of phases also. If the phases are constant, if the phase difference is constant, then addition of amplitudes carry a meaning. So to summarize, in case of coherent light we can say is linear in amplitude. Incoherent light is linear in intensity. Okay. So let us assume that because we are discussing interference, we will assume that the two beams which are interfering, which are superposing, are coherent between themselves, and we have to add their amplitudes and take the square modulus. So as we know, if we add two complex quantities, suppose x and y are two complex quantities, we add them up, and if we take the square modulus, this is how to get the intensity of the light beam, then what we do is x into x conjugate plus y into y conjugate plus x conjugate into y plus x into y conjugate. This is the result. So if we do the same thing here, what we get is, well, a square into e to the power I something into e to the power minus I something will only give you a square. So you have a square plus, here you will have b square plus, well, here you have A into, well, the product of these two, AB, into e to the power, let's say the conjugate of this first. So you will have, well, kz minus omega t will cancel out, and you will be left with I into delta 2 minus delta 1. Okay. And for this part, we'll have plus AB into e to the power minus I into delta 2 minus delta 1. Now let us say the difference between the phases. Remember, it is not the absolute phase that matters, it is the difference between the phases of two light beams which are interfering. That is of concern. The absolute phases may be anything, but it is the difference of phases which ultimately detect, which ultimately decide on the interference pattern that you get, the result of interference. So the result of interference I will be, so I is equal to A square plus B square plus, well, if we write this whole thing as delta, so if this is your delta, okay, this is your delta also, then it is AB into e to the power I delta plus e to the power minus I delta, which will actually give you 2 cos of delta. Okay, so this is the well-known equation for interference. I is equal to A square plus B square plus 2AB cos delta. Now let us look at some of the implications of this equation. Well, let us say, well, we can simplify this equation in this manner. Well, remember, A square is the intensity of the beam of one of the beam, B square is the intensity of the other beam. So we can write this as I1 plus I2 plus 2AB, we can write it as root of I1 I2 into cos delta. This we can further simplify as I1 plus I2. You take this out and you're left with 1 plus 2 root of I1 I2 divided by I1 plus I2 cos delta. Okay, this is what you get, and this is I1 plus I2 into 1 plus V cos delta, where V is equal to 2 root of I1 I2 by I1 plus I2. This is called visibility. V is known as visibility, and it is defined as well, visibility is actually the contrast of the fringes that you get. Okay, the difference between the bright and the dark. And so in a scene, I mean, in your fringe pattern, you have certain portions with maximum brightness, you have certain portions with minimum brightness, right? So visibility is defined as, or contrast or visibility is defined as I max, these are the region of maximum contrast, I max minus I min, and the region of minimum contrast, divided by I max plus I min. This is your contrast or V. Okay, right. So what is your maximum contrast here? This is I. Sorry, what is your maximum intensity that you can get? Let us find I max. I max equal to, well, all of these are A and B are fixed. The amplitude of the two beams that are interfering, they are fixed. What varies, V cannot vary because it's also a function of I1, I2. only delta can vary. Okay, so you will get I max when for delta equal to 0. Okay, so this is I1 plus I2 into 1 plus V, and I minimum will be for delta when the cos delta value will be -1, that is delta is pi, then this will be I1 plus I2 into 1 minus V. And then if you find out the contrast, so if you find out the contrast as I max minus I min by I max plus I min, you will be left with V only. So V is the contrast. Okay. Also, you can very well see that when for I1 equal to I2, that is A equal to B, right? The amplitudes of the two beams are exactly equal, that is the intensities are also equal. Then V, which is 2 root of I1, I2, let's say I1 equal to I2 equal to I. So we are left with 2I on the numerator, 2I in the denominator for the expression of V, and which is equal to 1. So for I1 equal to I2, V equal to 1. And if V equal to 1, then I max equal to 2 into, let us suppose that I1 plus I2, which is the sum of intensities of the two beams, this is I naught. Let us say this we represent as I naught. Then we are simply left with 2I naught. This is the maximum intensity, and I min is equal to 0. Because V is 1, so 1 minus 1 is 0. Okay, so this is the maximum intensity 2I naught and the minimum intensity 2I naught. Now let us try to plot this in a curve. Okay, let us say we have the coordinates as intensity. So on this side we plot intensity, and on the x-axis we plot phase. Okay, which is delta. Right, so from this equation you can see when delta equal to 0 and V equal to 1, let us say V equal to 1, so the maximum intensity is 2I naught, so this is 2I naught. Okay, the minimum intensity is 0. When is it 0? It is 0 at delta equals to pi. And how is the change? The change is 1 plus cos delta. Okay, which is simply something like this. It comes and takes a turn here, goes to 0, and then again if you increase the phase, it again rises up to the same point and continues in this manner. This is a 1 plus cos curve or cos square curve. You can express 1 plus cos in terms of cos square delta by 2. So you see this curve we get for V equal to 1. That is when the two interfering beams have the same amplitude. What happens when, okay, before that, in case of incoherent interference, incoherent superposition, that is the case when the two beams are not coherent between themselves, the result is simply, we have seen I1 plus I2. Okay, when they are not coherent, so here we see in this case they are not coherent, so this square will give you a square, this square will give you b square. Okay, if the two beams are of the same amplitude, then you have simply I naught, which is a square plus b square. So in incoherent case, what we have is simply a line here, okay, which is independent of delta. This is I naught. Now this, I'm sorry, this should have been a little down. Maybe this should have started somewhere here. Okay, this is I naught. So you see, when you are superposing two incoherent light beams, the intensity was I naught, which is A square plus B square. When they interfere, the maximum intensity have doubled to 2 I naught. Okay, so it's an increase of energy. So, but it doesn't violate conservation of energy because at some other point you get zero intensity also. So the average intensity remains constant. Now, this is true for V equal to 1. That is when the contrast of the two fringes, sorry, when the amplitude of the two fringes are exactly equal. What happens when V is not equal to 1? You see, if you look at this expression, the value of V can, yeah, the value of V can change between 0 to 1. Okay, this is a fraction. This is always a fraction. It cannot go beyond 1. So, for example, if V is half, that is the amplitude of the one of the beam. For example, if the amplitude of one of the beam is half that of the other, then V is some fraction. So V is some fraction means that your maximum intensity will never be 2 because V is a fraction, V is not 1. Okay, it will never be 2 and the minimum intensity will never be 0. Okay, in other words, we can say when the two interfering beams do not have the same intensity, then your variation of intensity with phase will follow a pattern like this, which will neither be a maximum, sorry, which will neither be a maximum nor be a minimum. It will go on like this. Okay, and this is supposed to be a sinusoidal, I mean cos square curve, but my drawing is going awesome. Okay, if you decrease V further, the maximum and the minimum would again come closer together. That is, in other words, the contrast of the fringes are decreasing. Okay, so to get maximum contrast fringes, to get very good quality fringes, what we have is the amplitude of the two beams must be exactly equal. Then the dark fringe would be absolutely zero, and the bright fringe will be twice the sum of the amplitudes or sum of the intensities of the interfering beams. Okay, so now that we have understand the requirement for interference, number one requirement is the two beams must be coherent. The second requirement is that preferably the two beams must have the same intensity values. Let us see what an interferometer is. So basically an interferometer splits up a beam of light into two and then recombines them. It attempts to recombine them together. Okay. We'll talk of a very basic interferometer. For example, let's say the uh, Michelson interferometer. Okay. Now we will do the Michelson interferometer. It's a special case with parallel beam of light. So let's suppose we have a parallel beam of light. Okay, I'm drawing a ray only now for the present. And let us say we have a beam splitter. A beam splitter is a optical device that it's a semi-mirrored plate of glass. Okay, that is to say, a part of the beam will be reflected because it is at 45 degrees. So part of the beam will be reflected up and a part of beam will be transmitted through this glass plate. And here you have a mirror. Okay, and this mirror is meets the incident ray at 0 degrees. That is, the rays normally incident on the mirror. The same happens in this case. So light is reaching the mirror, it comes back, and then it is directed towards a screen. Here both the beams are coming here, it is falling on the screen, and we get the interference pattern here, right? So this is a standard interferometer of the Michelson type, and we would assume, let us assume for the time being, that we have collimated the beam and the beam is a plane beam of light. So we have a plane beam of light. Let me use a marker here. Okay, so this is a plane beam of light going here, here, and coming back here. Okay, now let us assume for the time being, so if it's a plane beam of light, then we know that the wavefront is a plane wavefront. The wavefront is a plane wavefront. It means that, sorry, the wavefront is a plane wavefront. So what we see here is a plane wavefront. We had a plane wavefront here. What does a plane wavefront mean? A plane wavefront means you have a parallel beam of light. It's a parallel beam of light. Okay, so we have a plane wavefront. Now, parallel beam of light essentially means that you must have a point source. Otherwise, you cannot get a parallel beam of light. Either the point source is at infinity. For example, from stars, we get a parallel beam of light. Why? Because stars are so far that if this is a star, let's say, and this is a spherical wavefront that come out of the star. It's not spherical actually, because the star looks spherical. It may not be perfectly spherical. It has some, curvature of the wavefront, and this has propagated, let's say, uh, thousands of light years till it reaches us, and we are just a speck here. Okay, so for all purposes, what we receive is a parallel beam of light. So parallel beam of light is possible if you have a point source at infinity, or you have created a point source from where the light diverges, and you have put a lens here so that you get a parallel beam of light. So the location of the pinhole, or this point source that you have created, it can be a fiber end, it can be a pinhole. This has to be located at the focal plane of a converging lens. Then you get a parallel beam of light. So effectively what you have done is you have brought the infinity point to the focus of a lens. Okay. Now, so if this is the case, if we have, let us assume that we have these mirrors are perfectly flat. We had a plane wave front here, so we will have two plane wave fronts interfering. So on the screen, suppose this is my screen on which we attempt to see the interference patterns. You will see two wave fronts. Okay, this is one wave front and this is the other wave front. They are perfectly parallel to each other. So they will superpose on the screen. The screen actually causes interference. Okay, if you have no screen, the two wave fronts would propagate till infinity without any interference. To see the interference effects, you need a screen. You need to stop the beams on an absorbing surface to see the interference fringes. Okay. Now, let us assume that these two mirrors are perfectly parallel to each other. Therefore, these two wave fronts which come here from these mirrors, they are also parallel to each other. Let us also assume that one of the, from here, from the center of the mirror, this length is L1 and this length is L2. Okay. So the beam in the first arm, so this is the first arm, this is the second arm, the beam in the first arm travels L1 plus L1, which is twice L1. The beam in the second arm travels L2 plus L2, twice L2, so that their difference of their optical paths is 2 into L2 minus or difference L1, whichever is greater, we don't know. Okay, so that is equal to 2 into delta L. This is the difference of their optical, this is the optical path difference between the two beams that have ultimately come to the screen. See, after this, after the beam splitter, we do not need to calculate because they have traveled the same path. They will travel the same path till the screen. Before the beam splitter, we also need not calculate because it was one beam only. We only need to have the separation, the difference between the lengths of the two arms, twice of that. So this is the optical path difference. So if this is the optical path difference, as we discussed in the last class, what is the phase difference? The phase difference is 2 pi by lambda into the optical path difference, which is 2 into delta L. So this is your delta, right? Now, if this is my delta, if this is the phase difference, which is fixed, why it is fixed? Because these two arm lengths are also fixed. So the separation between the wave fronts, when they arrive at the screen, it is also fixed. And what is the separation? The separation is simply 2 into delta L. Now, if the separation is fixed, then the phase difference is also fixed, which is 2 pi by lambda into delta L. And let us assume that 2 pi by lambda into delta L falls, let's say, somewhere here. Let us assume that it is somewhere here. Okay, it can be at any point, but this phase corresponds to, let's say, delta is somewhere here. Now, it means that if it is somewhere here, you would get an intensity corresponding to this value, right? Which means over your field of view, you will have a single intensity. There are no fringes. Okay, there are no fringes. What we see is uniform intensity region. Everything is uniform here. It may be, we don't know what it is. It may be completely black. If delta is pi by 2, it is completely black. If delta is, well, let's say 2 pi, it will be completely bright because this leads to 2 I naught. Okay, it is, if it is somewhere in between, then it will be somewhere in between, some grayscale in between bright and dark. But there are no fringes. So the result of interference is always a fringe, is not a correct concept. We may get complete dark, we may get complete bright, or we may get an intermediate intensity between complete bright and complete dark. Now let us say what we do is, I'm redrawing the interferometer. Let me use this again. Okay, so this is my beam splitter, and this is the input beam. Sorry, this is the input beam. Well, these are the mirrors we have here. And this is a plane beam of light. I have drawn only a ray, but it is actually a plane beam of light. So the wavefront is something like this. Now this wavefront, I'm drawing the wavefront. Remember, wavefront is the surface on which the phase everywhere is the same. At any point on the wavefront has the same phase. Okay, in other words, they have reached the wavefront surface from the source at the same instant of time. They have the same phase. So this is also a plane mirror, and this is the incidence is perfectly normal. Okay, So everything is the same as in the previous case, where we are getting two parallel beams at the output. But now what we have done is, let us say we have inclined this mirror slightly. Well, if we have inclined this mirror, then what will happen is the wavefront that comes back will not follow this path, but it will be slightly deviated. Okay, maybe it will come back like this. So if it comes back like this, then its wavefront will also be slightly tilted. Okay, so one wavefront is this, the other wavefront, which is coming back from the reference mirror, which is not tilted, okay, will be a plane wavefront. I mean, both are plane, but this is untilted. So now we see that the two wavefronts are not parallel to each other. And something very interesting happens. So we have the two wavefronts which are not parallel to each other. So this is one wavefront and this is the other wavefront. They are not parallel to each other. Okay. Then what is the result of interference? Let us assume that at this point the phase is zero. Well, it may not be zero actually. It can be anything. It, so let us assume that the phase here is zero. The phase here, well, as the two beams are interfering on the screen, see this, they are arriving, they are superposing at different instants of time along its length. Okay, so this will be superposing earlier than the superposition of these 2 points, right? So let us say in this case the phase difference is no longer uniform. Say this is your pi phase difference, this is pi phase, this is 2 pi phase, this is 3 pi phase, sorry, this will be a straight line, and so on. Okay, now you can see that because the phase difference is zero according to our equation, which was I equals to I naught into 1 plus cos delta, we have assumed v equal to 1, which we'll always do in most cases. We see that when delta equal to 0, you have a bright fringe, so you have a bright fringe here. As delta keeps on increasing from 0, what happens? The intensity, the resultant intensity keeps on decreasing till at delta equal to pi, you get a dark fringe. Then you get a bright fringe again at 2 pi and a dark fringe again at 3 pi, and this continues. So now comes the concept of fringes. So when two wavefronts have a varying phase difference, and if the variation of the phase difference is of the order of 2 pi or greater, then only we can see fringes. So free water fringes, for example, if this is a dark band, this is a bright band, this is a dark band, sorry, this is a bright band and this is a bright band. So bright to bright is one fringe, dark to dark is one fringe. Okay, this is one period. Right. But then on the screen, suppose this is my screen, the wave fronts are interfering here. This is my screen. And the two wave fronts which have interfered, let us say they were, let me draw it once again. So that if this is one wave front, and if this is the other wave front, remember they are no longer parallel to each other. So let's say this is the other wave front. Okay, they are interfering between themselves and they are superposing on the screen. Okay, so they are now superposing on the screen. and we have seen that we will see fringes. Okay, the question is, this is my screen. This is my screen. The question is, what is the direction of fringes? Will they be directed in this direction? Will this be the fringes? Let's just assume that we are drawing only the dark lines. Okay, we know that the fringes would be bright and dark with a cos square variation between dark to dark and bright to bright. Will it be like this, or will it be like this? Well, what is the direction of the fringes? To answer this question, we will find we have to know what is a fringe. Okay, so this is a dark point. What we have done so far is just a dark point. So if this is one wavefront, this is the other wavefront, we have a bright point here, a dark point here, a bright point here, and so on. So these are just points. But what are fringes? Now, here, if you have let us assume that we have a dark point here. Here you have a dark point. And the phase difference between the two wavefronts here is pi. Now, wherever the phase difference over the wavefront, because this is a two-dimensional thing, a three-dimensional thing, in fact, the wavefront, it is not just the cross-section, but it extends over its surface. So, wherever we have a phase difference of pi, this dark fringe would continue, would extend. And in this case, we know that if this is pi, if these two wavefronts are plane, then the corresponding point on the other side must be pi. Therefore, the fringes must be extending like this, okay? Because everywhere along this line, the phase difference is pi. Everywhere along this line, the phase difference is pi. So we can easily say the fringes would be along this direction. Okay? In other words, the direction of the fringes in case of two plane wavefronts interfering, if one has a slight tilt, the direction of the fringes would be along the intersection line of the two fringes, of the two wavefronts. Where the two wavefronts interfere, all the fringes would follow that line if the two wavefronts are plane. Right? What about the spacing between the fringes? The spacing between the fringes would be equal. They would be equal. Why? Because the rate of change of phase is constant. Okay, it's kind of it's a triangle kind of a thing where, well, this is proportional to this is proportional to this. So the rate of change of phase is constant along the direction of the fringes. Therefore, the fringes would be equispaced. Also, what happens if we tilt the mirror a bit more? For example, if we tilt the mirror a bit more, then what happens? For example, if we tilt this by a greater angle, for example, initially it was like this, or initially it was like this. Now we have tilted it by a greater angle. Okay, what happens? The rate of change of phase becomes faster. Okay, so in this case, we might have got a dark fringe somewhere here. Okay, when it is tilted, maybe this is dark. When it is tilted further, the dark fringe comes here. Okay, so if you tilt the mirror further, greater the angle between the two interfering wavefronts, greater is the density of fringes. Density means number of fringes per unit length. Greater is the density of fringes. Okay. Also, suppose also one more thing is that let us say this is one wavefront and this is the other wavefront. Let's say you are asked to calculate the density of fringes given the angle theta. Well, we know that when the separation between the two wavefronts is pi, you get a dark fringe. Now pi means lambda by 2. Well, let's say here the separation was 0, so this is a bright fringe. When it is lambda by 2, it's a bright dark fringe. When it is lambda, so if this is lambda, if this separation is lambda, you get a bright fringe again. So if this is lambda by 2, then this part is lambda by 2, this part is lambda by 2. Okay, so between when the from the point first where the phase difference was 0 till the point where the phase difference is lambda, you are getting one fringe. Okay, where is the next bright line? The next bright line would come at, well, the next dark line would come at somewhere here, where this is lambda by 2 again. Lambda by 2 means pi phase difference, so this is 3 pi. So again you have a dark point, and then again the next bright fringe would be here, okay, where this is again lambda by 2. So you see, for every lambda phase difference, if these two beams are linear, I mean they have a plane wavefront, for every lambda you are getting one fringe. Bright to bright is one fringe. See, if the phase changes by one lambda, you're getting one fringe. So it is easy to say the fringe density if you know this distance. For example, you're asked to find the fringe density in terms of let's say fringes per millimeter. Okay, how many fringes will be there per millimeter? So what you do is basically take this as 1 millimeter. If this is 1 millimeter, this is theta. Okay, then this height within 1 millimeter, this is simply tan theta. This is, if the base length is b, then this is, or if this length is b, then this is b tan theta. If this is 1, this is 1 tan theta. So within tan theta, this height is tan theta. If this is tan theta, then how many fringes would be there? So number of fringes n would be equal to tan theta by number of wave fronts it contains, because every wave front, every separation of one wave front gives you one fringe. Two wave front will give you two fringe. So sorry, not the wave front, it's a lambda. Okay, so it's very easy to calculate the density of fringes provided you know the angle at which the two beams interfere. Well, next, what happens if the two beams that are interfering, they are not parallel to, they're, of course we know that what happens when they're parallel to each other, when they're not parallel to each other, but what will happen if one of the beam has a curvature like this? For example, one of the beam is spherical. Okay, one of the beam is spherical and the other beam is of course a plane beam of light. So we have introduced a lens or something in one of the arms, and one of the beams have become spherical. Then what would the fringes be like? Well, in this case, we would obviously get circular fringes. Why we would get circular fringes? Because this is a spherical beam of light. Okay, this is a spherical beam. It's a plane beam. So basically, it's a the phase here, and at the same position on the other side, and at everywhere, because it's a spherical beam, at everywhere on the other side, everywhere, okay, the phase is identical. So you will get another circular fringe here. Okay, and then these fringes will continue, but would the fringes be equispaced? No. Why? Because the gradient between the two beams is increasing very sharply as you are going towards the edge. Okay, the angle between the two beams decide the number of fringes. So as you are going outwards, the gradient is increasing very sharply. Okay, so as you are going outwards, the number of the fringe density will keep on increasing, and this is exactly what you get in Newton's fringes. So the famous Newton's fringe experiment, the fringes you see is basically the superposition of a spherical wavefront and a plane wavefront. Okay. Well, this is about normal interference, and well, as you know, in optics, interferometers is used for various purposes, and there are various kinds of interferometers. One we discussed is the um, mag. It's a modified Michelson interferometer. It's called the Twyman Green interferometer. Twyman Green. It's used for testing optics. You can have, it's a modified modified Michelson interferometer with a parallel beam of light. You can have a Michelson interferometer. Interfero. Okay, this is a modified Twyman Green is a modified Michelson. Then you can have a Mach-Zehnder interferometer. In fact, Michelson and Mach-Zehnder are the most common type of interferometers you would encounter in quantum optics experiments. Okay, so let us discuss the Mach-Zehnder interferometer a bit. A Mach-Zehnder interferometer basically, well, we have seen what the Michelson or Twyman Green interferometer looks like. The Mach-Zehnder basically is something like this. You have, uh, let me draw this first, then I'll explain it to you. Okay. So this is the incoming light beam. It falls on a beam splitter. Part of the light is transmitted, part of the light is reflected. This is a beam splitter, BS, semi-silvered surface, glass plate. Then you have a mirror here. This is a complete mirror. So the beam turns 90 degrees because the mirror is at 45 degrees. And here again you have another beam splitter. So what happens is this beam, a part of the beam is transmitted, the part of the beam is reflected from the beam splitter. At the input end, a part of the beam is reflected. It falls on a 45-degree mirror. It turns by 90 degrees. Okay. And here also part of the beam is transmitted, part of the beam is reflected. So in this case, in case of a Mach-Zehnder interferometer, it is interesting that we get interference both on this side. Here you have an interference pattern. Here you will also have an interference pattern. And it is interesting to note that if the interference pattern, let's say here, let us assume that it's a circular fringes we are having because of some, well, one of the beams have become curved, have a curvature, let's say, the slight spherical curvature. So the center of this is, let's say, bright. Okay, you have a bright center here. Let us assume. Then in this case, you will have a dark center. Okay, this will be bright. Why is this so? You have a bright center here, you have a dark center here, which means that these two fringe patterns that you will get, they will have a phase difference of pi between them. Okay, the phase difference of pi actually reverses the contrast. Bright becomes dark and that dark becomes bright. If you go back to the I versus delta curve, you will see this happening. Well, the question is why this happens. Well, uh, I do not have the time to discuss this, but let me tell you very briefly. See, the beam splitter is a surface like it's a glass plate with one surface mirrored. Okay. Let us say this surface is mirrored. Just let me just undo this. This surface is mirrored. Okay. So this is not fully mirrored, half mirrored surface. So basically, if you analyze this, you will see one reflection from the glass surface, from the air to glass interface. One reflection is here, other reflection is here, something like this. One reflection from glass to air, the other reflection from air to glass. And those who are conversant with Fresnel's equations will know that whenever you have a air to glass, for example, light is coming from air and it is falling on a glass plate, a denser medium. Okay, in these reflections below the Brewster angle, you have a phase difference of pi. But if it is reflection from glass to air, from the glass side, if light comes in, there is no phase uh, difference of pi which is introduced. Okay, I can very easily demonstrate this for normal incidence. Let's say for normal incidence, the reflectance, reflectance, amplitude reflectance is n1 minus n2 by n1 plus n2. So when light is coming from the air side, n1 is 1, n2 is 1.5. So the result of this is negative. So the amplitude reflection is negative. So, okay, it is minus 1 into something or minus of something. Now, minus 1 is equivalent to e to the power I pi. That is, you have a phase difference of pi. But when light is coming from the glass side, then it is 1.5 minus 1. So there is no minus 1. So no question of any pi. Okay, so now let us have a break for 5 minutes. We'll reassemble after 5 minutes then. Okay then?
Yeah, sure,
Yeah,
sir.
sure, sir.
Yes, sir.
Yeah, we'll reassemble after 5 minutes.
Yeah, sure, sure.
অনুপটার বাবা কি আপনার সাথে কথা বলেছে কতক্ষণ আগে?
ঘন্টার ওপর।
1 ঘন্টা উপরে ও ফোন পাচ্ছে না, সুইচ অফ বলছে, আমার বাবা বলে শরীর খারাপ।
এই ধরুন পৌনে তিনটে,
হ্যাঁ, আমার কাছেই তো এলো প্রায় ওরকম ছবি, দুটো
পৌনে
ছবি।
তিনটে
Hello.
Hello.
Hello, sir.
Yes,
Yes,
sir.
yes, sir.
Now
Now
fine, sir.
fine, sir.
Okay, so can we rejoin?
Yes, sir.
Yes, sir. Sure, sir.
Participants are
Participants are
already
already
there.
there.
Yeah.
This webinar is being recorded. This webinar is being recorded.
Okay, so till now we have discussed interferometers, which are basically two-arm interferometers. Okay, so basically you have two wave fronts which are interfering. So these are typically called two arm interferometers. In two-arm interferometers, you have two waves which are interfering. This is one class of interferometer, and in whichever way you make the two wave fronts interfere, there are various modalities, various optical configurations, and the name of the interferometer differs according to the person who actually designed it. So we have the Michelson, we have the Maxender, and we have various other, the Dyson. And if you go to any book on optics, optical instruments or optical interferometry, you will see there are various class of interferometers, but basically they all have the same principle that two wavefronts are made to interfere. And from the interference pattern, you have to decide. From the interference pattern, you decide, uh, well, if it is used for optical testing, if the interferometer if it's used for optical testing, what happens is, suppose you are testing a flat plate. So in this Michelson or trimandry interferometer, this is the interferometer. You have two mirrors, and here you put the test sample. So where you put the test sample, this is called the test arm. And this the other one, where you have a plain beam of light coming back, this is called the reference arm. So the test arm and the reference arm, the light from these two are made to interfere on a screen. Of course, these days you do not have a screen, you have a CCD here. CCD or CMOS device, a digital recording device. Okay, and you can see the interferogram on the screen. And it is not only sufficient to see the interferogram, but it is also necessary to interpret the interferogram. Okay, so from the interferogram, from the fringe analysis of the interferogram, we can easily find out if there is any defect in this flat plate we are testing. Let us assume we have a flat plate here, and the flat plate is not perfectly flat. The flat plate has, let's say, a dent here. And this dent is of the order of, let's say, lambda by 4 or lambda by 10 or whatever it is. Then what happens, as the plane wavefront from the beam splitter is traveling the interferometer, okay, it is getting distorted. So here it will be something like this. This is the wavefront which is going towards the mirror. Why it will be distorted? Because you see the optical path here changes. Okay, light travels faster in air, so this portion, the distorted portion of the flat plate, here light has to travel more in air and less in glass. I'm sorry, this will be just opposite. It will be like this. Okay, it has to travel more in air and less in glass, and therefore this portion of the wavefront will be advanced. Okay, it will travel faster. It will be slightly advanced. So the any impurities or now see, let's say this has a refractive index of n. The glass plate is a refractive index of n. So n into t is the optical path. So even if there is a change of refractive index, then also the optical path changes. If there is a change of thickness, the optical path changes. And we know that the phase change is 2 pi by lambda into n into t. And therefore, the phase between the two interfering wavefronts would change. The other wavefront, remember, is a plane wavefront coming from the reference arm. So it's always the interference between the plane wavefront and the distorted wavefront. The distortion of the wavefront corresponds to the distortion of the sample, right? Because the wavefront is passing through the sample. Any imperfections of the sample in terms of its thickness or its refractive index would be embedded in the wavefront shape. Because the wavefront shape is changing, the result of interference between these two wavefronts would give you a unique arrangement of fringes from which we have to find out. Now what I'm drawing is, let's say, only the bright portions. In between you have the dark portions. So if this is the fringe structure you have, from this fringe structure you can exactly find out the three-dimensional nature of the defect. Okay, and the resolution can go up to lambda by 2. Okay, which is quite large. If you are assuming, let us assume lambda to be 500 nanometers, so we can resolve up to 250 nanometers, okay, using this, and it can go even larger depending on your on the well accuracy of the interferometer. Accuracy means, you see, these mirror surfaces have to be perfectly flat, because if the mirrors and the beam splitters themselves introduce a distortion of the wavefront, which it can do if the surfaces are not perfectly flat. And when you're talking of flat surfaces, for example, if you do quantum optics experiments, flatness in optics and quantum optics would mean, well, lambda by 4 is the minimum requirement. What it means? It means that a flat surface, well, looks flat, but microscopically it is not flat. It is something like this. If you look under a microscope, or let's say you do the AFM of a flat surface, it actually has these variations of from flatness. Okay, it has certain roughness values. So if the peak to valley, this deviation is greater than lambda by 4, then it is not suitable for an interferometer, and therefore this interferometer optics is so costly. Okay, a simple 1-inch mirror, and also remember, these are front surface mirrors. The mirrors are coated on the front surface. We do not have the back surface mirrors. The mirrors are not coated on the back surface, because if they are coated on the back surface, then you will have multiple reflections. You will be basically working with lasers, so you will be having a reflection from the front surface. Lasers are strong sources, so we'll have two reflections, one from the front surface, one from the back surface. We do not want that. We want a single reflection. So it would be a reflection from the front surface only. That's number one. Number two, the surface should be perfectly flat. If the surface is not flat, then a reflected beam also assume this kind of a curvature. Okay? Right. So there are dedicated softwares to okay. So there are dedicated softwares, okay, to analyze these fringes, and they would give you the well, three-dimensional structure of the defect. And this is widely used in various applications. For example, this can be used in inspection of a let's say a silicon wafer. Okay, this can be used in inspection of very good quality mirrors. Now mirrors can come in lambda by 10, lambda by 20, and even in extreme cases it can come in lambda by 100 flatness. So the peak to valley variation of the mirror surface would be lambda by 100 in case of a lambda by 100 flat mirror. Okay, so the question is, we know that fringe to fringe, from one dark fringe to other dark fringe, the phase is 2 pi. Okay, and therefore if we know this, we can exactly find the nature of the defect using this kind of fringes. Okay, now if we want to have an insight of these fringes, it's something like, suppose we have a hill, let's say hillock, and we mark, let's say this is my sea level, and after every, let's say, 100 meters, we mark out along the circumference of this hill. Okay, now if you look from the top, then it will look something like this. If you take a helicopter and go to the top of the hill, then it will look something like this, assuming that the contour is spherical. If the contour is not spherical, for example, if it is spread on this side, it will look like this. So this is what a fringe is. The only difference being here, the fringe to fringe separation is lambda, okay, instead of whatever we have marked here, 100 meters or so. So it's nature's way of marking after every lambda, okay, along the contour lines. So you can understand that we can very easily come back from the contour lines to the original 3D volume from which these contour lines have generated. There are dedicated softwares. We can also do it manually, but I am not going into all this. Finally, when the defect is very, very small, okay, of the order of, let's say, lambda by 4 or lambda by 10, then you are not getting a single fringe, okay. There is no single fringe. So the two fringes, the two wavefronts were perfectly flat except for this very small variation of lambda by 10. Now lambda by 10 here means you would only get, there is no fringe because you would only get a fringe if it is more than lambda by 2, if the variation is more than lambda by 2. So what you would get is simply a variation of the intensity and nothing else, and from that you can deduce nothing. And therefore there's another kind of interferometry which is called the phase shifting interferometry, PSI, or phase shifting interferometry. Now phase shifting interferometry has the potential to evaluate phases of the order of, or optical path difference of the order of nanometers or even less. The principle is very simple. I'll tell you in a summary because we have another chapter to cover, which is diffraction. Okay, so we have I is equal to I naught into 1 plus V cos delta, the basic equation for interference. Now what we do is, in one of the arms of the interferometer, okay, for example, if this mirror is shifted by a length L, then the additional path is twice L because light has to go and come back. The additional path is twice L. So if the mirror is shifted by, let's say, lambda by 8, then the additional path it has covered, the light has covered, is lambda by 4. Lambda by 8 plus lambda by 8. Lambda by 4 means you have introduced a uniform phase difference of of pi by 2. So here, this is my first frame, and this is all digital. You have to do it digitally. Okay, you have to record it on the CCD. So this is my first frame without any frame shift. In the second frame, you displace the mirror by lambda by 8, so that you have a phase difference of, it is not delta now, whatever delta is a function of x and y maybe, so it is delta plus pi by 2. Okay, so delta plus pi by 2, this is I1, I2 would be I0 into 1 plus cos of delta plus pi by 2. Delta plus pi by 2 would be your minus V sine delta, and then again you have a phase difference of pi, an additional phase difference of pi, so this is 1 minus V cos delta pi by 2, sorry, and here again another phase difference of pi by 2, so this would be 1 plus V sine delta. So once you have these 4 frames, we have to store these 4 frames in the interferogram, and that is all. The rest is software. And what is that? We have to do pixel by pixel algebraic manipulations. For example, you see we have 4 unknowns or 3 unknowns, I0, V and delta. Okay, and we have 4 equations. So this, we can use the standard 4-frame algorithm, which says that, you see, I4 minus I2, I4 minus I2 is 2 I naught V sine delta, this divided by I1 minus I3, which is 2V I naught cos delta. So this is equal to tan delta. Okay, so delta equal to tan inverse of I4 minus I2 by I1 minus I3. So you can find out the phase, okay, pixel by pixel. You're doing this operation pixel by pixel till you cover all the pixels of the frame, and you store delta, whatever value you get is stored in the 5th frame. Okay, another frame you generate, and this will give you delta xy because you are doing it over the full interferogram, okay, which is now digitized in terms of pixels. You're doing it over the full interferogram, and so you can find delta xy. Okay, there is more to it, but I'm not going into the details. The If you are interested, you can consult any book on optical interferometry. I would suggest optical shop testing, SHOP, by Daniel Malakara, who is actually from a Mexican person. Okay, so this is a very good book for all kinds of optical testing. Now let us come to the last topic, which is diffraction. Also, we haven't we haven't touched on interferometry. Is a very vast subject. We haven't touched on many things. For example, there is one interferometer which is called the Febvre-Perot interferometer. Now, Febvre-Perot interferometer cannot be used for optical testing. Incidentally, this Twyman ring interferometer or Michelson interferometer, they can be used to find the wavelength of light. Okay, you can find the wavelength of light, or in earlier days the standard meter was described in terms of number of wavelengths of sodium D light. Now, how they did it was, you have this, if you move this by exactly 1 meters, if you move the mirror by exactly 1 meters, then you simply count. What happens if you're moving this? You're introducing continuous uniform phases. Okay, and you will see the fringes actually growing. The fringes are number of fringes are evolving from the center or sinking into the center. Okay, if the fringes are circular, you will see the number of fringes growing. So between 2 fringes, we know that it is lambda. Okay, so we need to find how many fringes would shift if we shift the mirror by 1 meter, and that would define the number of fringes of a particular wavelength. In that case, it was the sodium D line. How many fringes you would need to shift this by 1 meter is actually the number of wavelengths in 1 meter. Now, a physical 1 meter bar, whether it is made of invar or whatever it is, it can expand or contract, it can break. But once if you describe in terms of number of wavelengths, okay, it is a quantity which can never change. If you specify the wavelength, then it is fixed. Okay, so earlier it was in terms of the Standard meter was described in terms of the diameter of the wavelength. And you can understand it is also possible to find out the wavelength if you fix this, if you move this by a known amount, then how many fringes cross our field of view. From there, we can easily find the wavelength because we know that fringe to fringe, from one fringe to the other, it is one wavelength. Okay? Okay. So let me go on to diffraction. Well, what is diffraction? We all know that diffraction is the bending of light when light encounters a sharp aperture. So if you have a very sharp aperture here, for example, it can be a pinhole, it can be a slit, it can be a slit, okay? If light is incident on this aperture, now everything is opaque except the center, except this. This is the white means it is transparent, it is fully allowing light to pass through, and black means it is completely opaque, okay? So what we expect is, we expect to have, according to geometrical optics, we would expect that, well, only in this region we would get light, okay? If you put a screen here, you would get light, only a circular patch of light if it's a circular patch, and here you would expect to have just a replica of the slit, okay? Because light cannot pass through other regions. But strangely, what happens is, here you would see a pattern which is something like this. Now, the y-axis is brightness and the x-axis is spread. Maybe the circular aperture would have been simply like this. It have been, this was a circular aperture. So you see, light have spread out beyond the geometrical shadow region. Here also, what you would expect, what you would see is just, this is the geometrical shadow, the rest is geometrical shadow, but light would spread out beyond the geometrical shadow region, and you would see the geometrically, propagating light, and also some fringes on the side. So light will be spread out in these regions also. This is called diffraction. Okay. Why this happens is, well, we do not need to go into that why this happens, but you can understand if you have a let's say you have a sprinkler, you have a source of water, and you have a aperture, very small nozzle, then naturally water will spread out beyond the region of the aperture, okay? So this is diffraction. In case of light, this is diffraction. But here there are many things which are very, very important. I will not be able to do the complete derivations, but I will just mention a few things. Okay. It can be shown from the diffraction equation that if you have an aperture here, let's start with a grating, okay? Let us say we have a grating here. And let us say we have a parallel beam of light illuminating the grating. Now, if we have a parallel beam of light illuminating the grating, let me do it with okay. So if we have a parallel beam of light illuminating the grating, for example, let us say, I'm sorry, let's say we have a beam of light and this is falling on a grating. Just hold on for a minute. Yeah, we have a grating here. Then what we'll see is, now this beam which is incident to the grating, what will happen to this beam is, this beam is, a part of the beam is going to go straight, okay, in the direction in which it was traveling, and then you will have several orders, okay, one here, the other here. This is the first order, plus minus one first order. This is the diffraction terms you have. You have another order going in this direction, okay, and there can be infinite number of orders, okay. Now what happens if you put a screen here? Let's say you put a screen here. If you put a screen here, you can almost see the shadow of the object. This is my object. In this case, it's a grating. Okay. So at a very near point to the object, you can see the shadow of the object, but then there are multiple shadows, not one, and they will overlap on each other. So to create a fuzzy kind of edge of the object, okay, if you move here, the fuzziness will increase, but maybe you could still recognize the object. But you see, in this, beyond this region, all the diffracted orders, they are going in their different paths, okay. So if you put a screen here, you would only be able to see some spots of light and nothing else. That is all you need to see. All you will be seeing, some spots of light and nothing else. Now these parallel beams, would meet at infinity, because we know that parallel beams meet at infinity. Okay. So at infinite distance, we would simply get an array of delta functions, that is points. According to the diffraction equation, as I said, we are not going into the details of the diffraction equation, but according to the diffraction equation, the diffraction pattern at a very large distance from the object is nothing but the Fourier transform of the object. So here this is my object, the grating is the object. At a very far distance, what you get is simply the Fourier transform of the object. Okay. The zone between the object and where the beams are still overlapping, so that the object may be recognizable. Each edge of the object is now fuzzy, it's spread out because of the multiple shadows, multiple beams traveling in different directions, each carrying the shadow of the object. Okay, so the edges will be spread out, and if the edges spread out, you may be able to find out the nature of the object. But beyond this point, each of these parallel beams are going in their respective directions. So this is called the Fresnel zone, and beyond this we have the Fraunhofer zone. And the far field diffraction pattern is nothing but the Fourier transform of the object. And what is the Fourier transform? The Fourier transform, for example, if you have an object OXY, so if you write an object OXY or FXY, what does it mean? It means the amplitude of the object at the point XY varies according to FXY. So if the object is fxy, let's say, then its Fourier transform is given by e to the power minus I twice pi into ux plus vy dx dy double integral minus infinity to plus infinity. Now, we are more accustomed with Fourier transform in the time domain, okay? Twice pi ft, where the argument of the exponential is minus I twice pi ft. But here, remember, in time domain, if it's a voltage fluctuating or the whatever is fluctuating with respect to time, there's only one parameter, time. But here you have an object, so it has two parameters, both x and y. And corresponding to these two parameters, you have two spatial frequencies. Now, this was temporal frequency. In this case, it was hertz, temporal frequency. In this case, it is spatial frequency, which is number of lines per millimeter. Okay. So with this concept that the far field diffraction pattern is nothing but the Fourier transform of the object, which it's beyond the scope to derive this. Neither we have the time. Okay, but any book on optics will give you this result. We can see. Let us find out. Well, let's say what this. I mean, what is the use of all this? Okay, so let us take two examples. For example, let's say we have a grating. We have a sinusoidal grating. Now, a sinusoidal grating means a grating where the variations of, well, it is not just simply bright and dark. I mean, transmittance and no transmittance. So if you plot along the lines of the grating, it is not just simply maximum transmittance and zero transmittance, maximum transmittance and zero transmittance. This is not a sinusoidal grating. This would be more like a square top grating or rectangular grating. Okay. Now these kind of gratings are more easily available. But if you have a grating, so what we are plotting is the transmittance on this side and the distance on this side. Okay. If we have a grating where the transmittance is something like this, it's varying sinusoidally. Okay, it's not 0 1 0 1, it's varying sinusoidally. This is a sinusoidal grating. Okay, and like well, like you have if what does the Fourier series say, or the Fourier integral? Well, it simply says that any object can be thought of, or any waveform in time, okay, periodic or aperiodic, it doesn't matter. It can be voltage versus time, it can be something like this. This can be expressed in a Fourier integral, which means this can be expressed the summation of various cos and sine terms, cos omega t and sine omega t terms, with well, fundamental, second harmonic, third harmonic, fourth harmonic, and so on. And if this is continuous, as it is shown here, if it is periodic, then the harmonics will be discrete, which is you have omega, twice omega, 3 omega, 4 omega, and so on. But if this is aperiodic, then you will have infinite number of frequencies. Okay, so the basic unit is sine omega t and cos omega t. These are the basic units with which you constitute this particular function. Okay, in case of an object where you have x and y, okay, the basic unit is a grating, which is given by half into cos of 1 plus twice pi ux plus vy. Now, I know this is getting complicated, but let us go straight away to find the diffraction pattern of a slit. So let us say we have a slit. Let us say this is my slit. Okay, and we want to find the diffraction pattern of a single slit. So what do? We simply need to find the Fourier transform, because the far field diffraction pattern is the Fourier transform. So looking at the Fourier transform, can we find out the dimension of the slit? This is what is interesting. Dimension means this dimension, the width of the slit. The height is, we'll consider it to be infinite. We'll only consider the width of the slit. And the width is usually, for slits, the width is very small, of the order of, let's say, 100 microns, 10 microns. It can even be 1 micron. So what you do is you take the slit, okay, and you shine light on it, and you put a screen after a certain distance z. Look at the pattern. The pattern will be something like this. And looking at the pattern, is it possible to find out the thickness of the slit? The slit is very small, of the order of 1 micron, let's say. Now, let us say the slit is in the x direction and it is from minus a to plus a. The width of the slit is 2a. Okay, and this is my object fxy. There are various ways of doing this calculation, but let us do it with Fourier transform. So what is the Fourier transform? The Fourier transform, I mean, it's better to consider only one dimension for ease of simplicity. So fx, because y is infinite. So for a one dimension object, well, what is the Fourier transform? The Fourier transform of the slit is equal to integration of minus infinity to plus infinity. If the slit is represented by a function fxy into e to the power minus I twice pi into ux dx. Okay, because we are in the space domain now. So omega is replaced by u. What was omega? Omega was number of oscillations per second. Here you have number of oscillations per unit distance, and time is replaced by x. Okay, now the slit exists only between minus a to plus a. Even though our limit of integration is minus infinity to plus infinity, the slit exists only between minus a to plus a. So this is equivalent to minus a to plus a. The slit is defined as within minus a to plus a, the transmittance is 1, fxy equal to 1. All the light is transmitted. Beyond that, no light is transmitted. So fxy between minus a to plus a, fxy is 1, and you have this kernel of the Fresnel of the Fourier transform minus I twice pi ux dx, right? Then if you carry out this integration, this would simply be e to the power minus I twice pi into u of a minus e to the power minus, well, plus will be here, twice pi u of a divided by minus I twice pi u. Okay, now what is this? If you remember, e to the power ix is equal to cos x plus I sin x, right? So we will have minus, and if this is minus, you get a minus sign here. So from these two, this would be minus 2i into sine of twice pi ua divided by minus I into twice pi u. Okay, so I cancels out, the negative sign cancels out. Okay, well, let us keep the 2 for the time being. So this is equal to, you can write 2a into sine of twice pi ua by twice pi ua. So we have just multiplied a in the numerator and denominator, and this is equal to 2a into a sinc function with the argument twice pi ua. So if you're asked to plot this, it would simply look like, if this is my sinc, so this is the amplitude of the output. Okay, this is not the intensity. To get the intensity, you have to take the square modulus of this. So this is the amplitude. So you see, at twice pi ua, suppose we are plotting this with respect to twice pi ua, this is equal to 0 here. At 0, sorry, at twice pi 0, this is equal to 1, because sine sinc of 0 is 1. Okay, so this would go on like this, and you get the first 0. The first 0 would be formed when 2 pi ua is equal to pi. Okay, the first 0 on the other side would be formed when this is also equal to minus pi. And what you would get is, in the screen you would see a bright line, then it is gradually going to dark, then again a brighter line. So because this will continue, again you will get a bright line. So you just need to measure the distance between the first 2 dark bands. The distance between the 2 dark bands, is only this much, which is 2 pi. So if this is 2 pi, okay, if we measure this, let us say this distance is, we have measured to be, let's say, x naught. Okay, the question is, how do we introduce x naught here? Because you have to remember, from the last class we have seen that u is equal to x by lambda z. What is z? Well, z is this is z, the distance of the screen from the slit. So z we know, we have already measured z. Okay, lambda, the wavelength of light, we know. Let us assume that we know. Then if we can find the separation between the two, first 2 dark bands, then we can easily find a, which is half the, or twice a, which is actually the dimension of the slit. Okay, also, if the dimension of the slit is known to us, here look, if the dimension of the slit is known to us, for example, if a is known to us, then the equation is now, my board is stopped working. Yeah, so if a is known, then you have 2 pi into, what is u? U is x by lambda f into a. Okay, now x we will measure from dark to dark. A is known to us, Z, this is not F, this is Z, okay? Z is the distance we have seen. So everything is known. So we can easily find out lambda. We can find out the wavelength of light. So using diffraction, for example, as I said, there is not much scope to go into the details. So this is the diffraction of a circular, of a single slit. If you have a circular aperture, the diffraction of a circular aperture is nothing but a Bessel function like this. Okay, it's a Bessel function. And this actually leads us to a very interesting thing, which is diffraction in imaging. Which will ultimately lead to the Rayleigh criteria for imaging. So I will just discuss this as the last topic today. For example, you have a lens. A lens, we all know, is a circular, has a circular aperture in, well, 99.9% of the cases. We have a plane beam of light. Let's say we have a plane wave front which is illuminating the circular aperture, containing a lens here. This is a lens. So what will happen is the lens will focus the light somewhere here. Let's say somewhere here. Sorry. Where we are expecting a point. But as we have seen, this will never be a point because of diffraction, as the wavefront passes through the lens, it will not be a perfectly spherically converging wavefront, but it will have some distortion at the edges. Okay, so the wavefront will ultimately look like this, maybe. Sorry. Which means that it will not come to a focus. It will be, you will get a series of circular bands here, and this pattern, as you know, is called the Airy pattern. Okay, this diffraction you cannot avoid. It is impossible to avoid diffraction. It is a natural phenomenon. You can design the lens so that, as you know, lenses can have aberrations. A very good designer can design the lens so that the aberrations goes to a minimum. Okay, it is almost zero. So it's a very good lens system where the aberration is zero, but you cannot avoid diffraction. So lens systems where the aberration is zero, but the limitation in imaging is only because of diffraction, is called a diffraction limited system. So the diffraction limited system, diffraction limited system. So diffraction limited system is the best optical system that you can have. It has no aberrations. The only limitation is diffraction, which you cannot avoid. And a diffraction limited system is what all lens or optics designers attempt. In fact, in your if you are doing experiments on quantum optics, you need to have diffraction limited systems, just for the simple reason that you do not want aberrations to introduce additional unwanted phases. Aberration is just an unwanted phase. Okay, you do not want unwanted phases to affect your photon. Now, the pattern we get there, if you, it's a circularly symmetric pattern, of course, because the lens is circularly symmetric. The pattern you get there is also circularly symmetric. And if the pattern looks like this, and if we plot across the cross section of this pattern, okay, then you get something. This is what you get. If you plot the intensity across the cross section, this is what you get. This is called the Airy pattern. Airy pattern. After forbidden Airy, So what we're expecting to be a point is now a patch of light. Okay. So if you are imaging, well, if you have an object here, an object is a collection of points. Object is nothing but a collection of points of different intensity values, different amplitudes. Now, if each point is spread out like this, then you can very well understand the details, the resolution of the object. You cannot have full resolution of the object. And from here, we come to the concept of Rayleigh criteria. Okay, we know Rayleigh criteria. If you don't remember, I'll request you to go back to your textbooks. Rayleigh criteria is in every optics textbook. But what is important, I want to stress here, is Rayleigh criteria says, just hold on for a minute, Rayleigh criteria says that the minimum resolvable distance L minimum is equal to 1.22 lambda f by d. This we also discussed in the last class. But this simple, very simple relation, which is easily derived from the Airy pattern, okay, this simple, very simple equation has a tremendous implication. For example, what is our target? To get good imaging, we need to minimize L minimum, right? The lesser the value of L minimum, it means we can resolve smaller and smaller structures. And how do we do that? By reducing lambda. Okay. Well, d by f is a factor which cannot be increased beyond a certain value. So 1.22 lambda f, the variable is lambda. The others can be optimized, which actually tells you that if you use UV light for imaging, you will have a greater resolution compared to IR, infrared. And that is why you will see that all these VLSI circuits, when they are transferred, photo etched on the wafer using a mask, using a process called photolithography. Okay, first you need a mask to transfer the pattern. It is all done in UV because we want to have very high resolution. The distance, the separation between two lines would be half a micron or even less. Okay, so to achieve that, we need to minimize lambda. Well, so in the optical domain, we can have from UV to IR, but then what happens beyond that? What about X-rays? Well, we do not have proper imaging setup for X-rays, so we cannot use X-rays. What about gamma rays? So when we are going on this side of the electromagnetic spectrum, we are trying to decrease L minimum further. Well, for gamma rays also, we do not have imaging materials. Then finally, we go to the de Broglie equation, which says that an electron, which is a charged particle, has a momentum associated with it. Okay, and it has a wavelength. And if you calculate this wavelength according to de Broglie's equation, you will see this wavelength is about 10 to the power minus 3 times the wavelength of light, which is you can increase the resolution L minimum, the minimum resolvable distance. You can decrease the minimum resolvable distance by 10 to the power 3 times. That is, you can increase the resolution, which is the reciprocal of L minimum, by 10 to the power 3. Okay, so this relation just gives you a cue that if you use electrons as imaging radiation, then you can go to further very high resolution, about 10 to the power 3 times resolution than UV. And this led to the evolution of electron microscopy. So electron microscopy is just a derivative of light microscopy. Okay, the whatever we studied in the last class, that is simple optical microscope. Electron microscope is the same parameters. You have a microscope objective, you have an eyepiece, everything, not the eyepiece exactly, but something else. But the configuration is the same. The only thing is that instead of glass lenses, you have electromagnetic lenses. Okay, it's a electro, because these are electrons, charged particles, we can deflect it using a magnetic field, and these magnetic fields are well generated using very complicated set of coils which actually converge these and diverge these and collimate these. Okay, so I think that is all. Well, each of these subjects are, it has a tremendous breadth. We have only touched a very few part of these. Okay, just the tip of the iceberg. So thank you very much. If there are any questions, then please go ahead.
Participants, any questions? Any questions?
No, I think. Anyway, if you well, you can also ask later. Okay, you can get my email, and you can
Yeah,
always
participants can, they can send their email.
yeah,
I
definitely,
will,
definitely.
I will pass it back to you. I think. Yeah, it's more or less. Thank you. Yes.
Okay, I'm then closing the.
Thank you so much, sir, for your valuable time and for the field explanation. Yeah, Chandrasekhar studies with me. Very in-depth
Okay, so my part is over now. Yeah.
Yes, sir. Thank you so much, sir. I request you to share the material and a few questions. The
Materials and
that can be given as quiz.
materials and questions. Someone is raising their hand. Pushpender.
Pushpender, I think they are appreciating. Thank you.
Okay. Understand. Okay.
Pushpender, you want to ask any question? No, I don't think. Right.
Okay.
Thank you so much, sir. We'll get in touch. I will talk to you regarding the
Sure.
material.
We'll be in touch. Okay.
Pushpender is thank you.
Then. I hope well, I could communicate something to the students.
Sir. Fully detailed.
Thank you. But you see, these topics are so, huge. I don't. It's very difficult to summarize, because even summarizing is very difficult. Okay. But anyway, if they have got the flair
Gist
of it,
of-
then they
gist
can
of-
develop on it on their own.
Yes.
Okay. Okay then. Thank you.
Right. Thank you so much. Thank you so much.
Bye.